Hi, everybody. I'm Heather Beadle. I am an assistant professor at the University of Oklahoma. This is my beginning of my third year there. And the University of Oklahoma is lucky enough to have some academic licenses for Geophysical Insights Paradise software. So I thought I would show a couple of case studies that my graduate students have been working on. So I'll be showing some work by Julian Shannon, who will be getting his master's in December, I hope. Corellia Lamarca and Carol Buist, who both got their master's in the spring and are continuing on with me for their PhDs. So I've got 4 case studies that are a little bit further along than some other studies, and I'll just go over them for, about 10 minutes each or so, just to show you some of the variety of what we're trying to use SOM for. So I'm going to start off with gas hydrates. This is work Julian first part of his master's. And to kind of give you guys an intro to gas hydrates, so these are gas hydrates are where you have a methane molecule trapped in an ice structure. These form in different pressure temperature conditions, a lot of times on the continental slopes or in the permafrost. And so they tend to occur in the area that we're looking at in New Zealand. They tend to occur between the seafloor and, well, you can see a nice DSR right here. Okay, and so you'll have these gas hydrates forming in the pore space. And what's interesting about them in a hydrocarbon sense is that they can act as seals and traps for larger hydrocarbon accumulations, which is thought to be causing some of these bright reflections here and over here. And so what I got curious about and what I got Julian curious about was thinking about, is there a better way to image these hydrates? Because we aren't able to see them in seismic data, but rather what we see is what we call the BSR, or a bottom simulating reflector, that ends at the base of the gas hydrate stability zone. And I know you guys can't see me because I don't have a video on this computer, but I'm like using my hand to demonstrate, and I should use the mouse. So this is an example of a BSR. So you have the area from the seafloor down to a certain temperature pressure where the gas hydrates are stable, and in that solid ice kind of formation below that, they act as free gas. And so when you go from an acoustic impedance regime where they are stable to where they are unstable, you get a larger reflection coefficient, which reflects the seismic energy back up, and that forms what we call the BSR. And so this is an example schematically of what that would look like. But what's interesting is that not every area where we have hydrates on Earth do we image a BSR. And so particularly in the Pegasus Basin of New Zealand, so here's the North Island and the South Island, and then here's the Pegasus Basin, and in pink I'm showing you the line that we're looking at right here. In the Pegasus Basin, it's really, really interesting. It's well studied. There's some 2D seismic there. I hear there's some 3D, but I haven't gotten my hands on it yet. But you can see that in some areas you have a nice strong reflector, a nice strong BSR, and in other cases maybe you see it. It depends on how you squint or not. And so we're curious, does that mean that there's no hydrates in this area, or is there just no free gas below the hydrates to let us see a strong BSR? And so we thought this would be one of our first examples where we tested out SOMs to see if the SOM results with the multi-attribute analysis would be sensitive to perhaps some of the attenuation or frequency changes that are happening in the areas where there's hydrates. And so here's a nice slide that Julian put together. We're working, like I mentioned before, in the Pegasus Basin. We actually have 2 2D surveys in this area, the PEG-09, which is shown in red, and then the APB-13, which is in a tighter 2D grid. And so this was a great case study for us because we could run SOMs on the PEG-09 data and then see if we could replicate the results on the APB-13 data that was shot like 4 years later. And so this is Pliocene sediments, kind of zoomed out. You can see the Pacific plate subducting underneath I think it's the Australian plate, and we're kind of in this frontal anticline area where you can see the BSR. And we've got if you zoom into this blue box, we've got nice strong BSRs here and here, and then these weak discontinuous BSRs that we're super curious about between those two. And so for the workflow that Julian came up with, the first thing he did was he imported the data into ASPE, Petrel, and Paradise, ran some attributes, tried to understand in his mind what was going on, and then move all of that into Paradise to run a PCA to see which were the more important attributes that should be used for the SOM analysis. After that, he tried to optimize the parameters, looking at the number of attributes we should run, the number of epochs, the number of neurons, that type of information that you guys are probably familiar with. And then he did some mapping. And what he did in the Pegasus Basin after that was, with the results, he mapped where he could see the BSR with the traditional amplitude interpretation, so the regular amplitude data, and then also with his SOM enhanced interpretation. And then we'll talk about some other results also later on for the last case study that he did. So like I mentioned before, if you have hydrates present, you can have different reflection coefficients happening depending on if there's free gas below them or hydrates above them. So if you have a high amplitude BSR, typically in this area, you have the hydrate column above it, free gas below it causes a large drop in the reflection coefficient, so you get a nice bright amplitude. In the areas where you have a weak BSR, we think the reflection coefficient is much smaller because you don't have that free gas below it, minimizing the FCPs in that area. And then in the area where there's no hydrates, you wouldn't expect to see any reflection because there's no change in the acoustic impedance between the sediments above it and below it. There's no hydrates in the pore space. And so we were able to look at these results. We had some angle stacks, but not gathers. So Julian was also able to run some ADO attributes like flow factor and instantaneous gradient and that type of stuff. And so just to kind of get to the results, here we're looking at the Pegasus line 19 that I had outlined in pink on a previous slide, and kind of the weak BSRs are in this red box. And so you could look at the seismic amplitude and then the raw results in the SOM, which of course hide what we may be interested in. So we just turned on a few neurons that seemed most interesting. And here's some of the results from the different neurons, which I have the attributes that go into them that I'll show in a few slides. But we noticed that a couple areas seem to be highlighted here. And so what Julian ended up doing is, we thought, okay, things seem to be working well. Let's try to optimize our SOM. Optimize meaning the number of epochs and neurons that we're using, as well as the different attributes. And so here's a case where we have an unoptimized SOM. So we're running, what is this, like an 8x8, it looks like. And then down below in image C, he just turned on a few of the neurons that seem to be most revealing and in the region of the expected BSR. And so we're pretty excited about this because it seemed like this red neuron number 50 seemed to be highlighting where there could be a very weak or discontinuous kind of indistinct BSR. And so after that, he optimized the SOM, cut down the number of neurons, the number of attributes, and got this result shown here down in F with just 3 neurons turned on. And so we're thinking that this is one way that we may be able to help distinguish these very weak BSRs. Looking at 2 intersecting lines, kind of shown up here in the upper right-hand side, we've got line 6 and line 19, some green arrows to highlight the strong BSRs, which clearly show up when you look at all the neurons, and then just turning on the few that we were interested in. And while you see some other stratigraphy in the area of the weaker or discontinuous BSR, we do see that these neurons seem to be highlighting a feature that could be that hidden BSR. Like I mentioned before, we had a second seismic survey, the APB, that's in the same area. And so we wanted to see if we could take this technique and the same parameters and get a similar result, you know, like a reproducibility of the science and the method. And so this is looking at two inlines and two 2D lines that are perpendicular and in the same area, the one I just showed you. And so using the same method, he was able to replicate some of the results kind of shown here, where the weak discontinuous BSRs are highlighted by the orange arrows. And so we're pretty optimistic that the SOM method is giving us some good results to help image the BSR. Just a few notes on the eigenvectors and the attributes that helped out. You can compare the Pegasus 09 with the APB 13 and see that the instantaneous and the thin bed were high contributors in our SOM analysis. The other ones that we used were sweetness, the gas indicator, and the Shuey fluid factor, which are AVO attributes. And so overall, our takeaways were that the PCA results for both models were nearly identical, with just small discrepancies. So that's great for reproducibility. The SOM clusters that seemed to highlight the weak discontinuous BSR were identical. And so we were glad to see that this method was transferable between two surveys in the same basin. What he did next was he mapped a traditional amplitude interpretation, just mapping on the full stack. And so where he saw the BSR with confidence, interpretation confidence, he mapped in red. And then you can see in yellow are areas where the machine learning SOM method helped him extend out where he thought those hydrates could be located with that weaker BSR. And here's it. So we were pretty excited about this result and being able to use SOM analysis to help us better map BSRs related to hydrates in New Zealand. So the next example I'm going to quickly show is looking at some pinnacle reefs, and this is some work that my student Carl Buis was doing as a master's, and he defended in the summer, and now he's working on finishing up this study, adding a few more details in order to create a manuscript out of it. So up in the Michigan Basin of the United States, there are quite a few pinnacle reefs, Devonian in age, and we have access to a couple of small, very small seismic surveys that have been shot in the last 5 years or so by Consumers Energy, which is a natural gas company. Carl, for this work, focused primarily on the Putty Gut 3D data, although he did look at IRA and Lennox, but I won't be showing you those results just for time today. But again, he developed a method over Putty Gut, and then he wanted to make sure it was transferable to IRA and Lennox, because I like to teach my students that science and methodology should be transferable. So here's a zoom in of the Putty Gut Reef. This seismic survey was shot in 2019. We have pre and post stack migrations. There's a couple of 18 wells or so, no, 30 wells that have gamma ray, 18 wells that we have core descriptions, and then 5 where he had core profile data. We were given formation tops and some horizons from Matthew Ryan, who works for Consumers Energy and helped provide us with this data. And so here's just the time structure map of the reef, and then what it looks like in seismic data. And so what I'll be talking about, for the next 5 minutes is how Carl tried to use SOM analyses to see if he can come up with any ideas about the internal structure of the reef. Do the SOMs provide us with more information about the internal structure and facies than just a single attribute analysis? The company, Consumers Energy, they're of course interested in porosity and permeability, and the SOMs could help us with that, which we didn't quite get super definitive data for. Oh, you guys lost my PowerPoint? Uh-oh. Well, hopefully it comes back up. I have bad internet. Oh, man. Okay, but so anyway, so Consumers Energy wanted us to see if we can have any ideas about what's going on with porosity and permeability, and that we weren't super confident in the results for, but we're still working on it. This is the workflow, a very simplified workflow that Carl came up with to work his way through those reefs. The first thing he did is, student projects, you gotta teach you guys all the right stuff to do. So you load the data and you do QC work. You try to understand what's going on. I look at the files and the headers and see if there's footprint and all of that super fun stuff. Next thing he did was run single attributes, which I'll show you, and then he did some well ties to try and understand what the attributes were telling him about the physical rock properties. He wanted to do a mini study looking at what happens in a SOM analysis with geometrical attributes as compared to more frequency-based attributes. So I'll show you two different SOM results. And then he did like the PCA analysis and created what he calls his best SOM, where he compared that to the well data to try and understand the relationships between the rock properties and the neurons. And so I've just got a couple of slides on this project to show you. So if you want, you can go to the next slide. And so what he did is he did this for the putty gut data, and then he also compared it to two other reefs, which I won't show you for time reasons. All right, can you go to the next slide, Laura? Or did you? Okay, so here I'm not going to focus on this too much, but here's some of the single frequency attributes that Carl selected on the brown horizon through the reef. And you can see clearly, even on like the two-way time map, where you have the reef and the non-reef structures. And then he looked at some different amplitude and frequency attributes, tried to look for features in different frequency domains. I've got a little box covering it, but I think it's like 29, is it 29, 57, and 81 hertz. Next slide, please. So here on the next slide, I think I'm lagging a little bit, but are the putty gut well correlations with the SOM. Hopefully you guys can see that. And so what we have here are some of the well data, and then he plotted on it some of the main neurons, and that's kind of in the center box of the well. And so what he noticed in the neurons that he was looking at in particular, that neuron 23, which is the bluer color, the dark blue, tended to show up in areas where he had the highest permeability and porosity. And then two other neurons that you can see in the left well in those yellow boxes were neurons 10 and 25, which he found consistently in areas where there was what he classified as good to great porosity, but then varying permeability. And then in the green box, he's showing neurons like that brownish color neuron where he had intermediate to good porosity, but varying permeability. And let me just move forward for time. So then on the next slide, you should be seeing cross sections from a previous study of Garrett in 2016 that show cross sections of the porosity and permeability. I forget the details of the Garrett study. I think he did some sort of reservoir analysis just based more primarily on seismic and the well data. And then below those two, Carl's showing his SOM results with just a few of the neurons turned on. And what he noticed was this blue colored neuron that you see on either side seemed to tie in well with areas that had higher permeability and porosity. And then if we go down to the next slide, which, and that's my last slide for Carl. So what he did after this is he just compared it to two different other surveys. And he found some decent correlations between what he could do in the SOM analysis and porosity and permeability. But this, to some extent, is still a work in progress, with some of the work being currently worked on. Okay, so next one I wanted to show was a study on channel architecture. And so this is work that Corellia Lamarca did. She's now currently a PhD student, but this was part of her master's student last spring. What spurred this study is she wanted to do kind of an analysis on what would happen if you compared user versus machine selected attributes. And so I'm just going to show you the machine selected attributes because we ran a PCA analysis on that in Paradise. For the data set that we chose, it's in the Taranaki Basin, which is just offshore New Zealand, kind of on the west side of the North Island. You can see that on the upper left-hand side of the map. We chose this data because New Zealand has lots of beautiful public data sets on, with really good quality 3D seismic surveys. And so it's a deep water setting. And if you go to the next slide, this is just what the data looks like. So in the vertical section, we're showing the seismic amplitude. And then I think it's variance being shown on the time slice. And so you can see some of those channel features in the variance. So this data was acquired in 2013, 0 phase, SEG negative polarity. She had one well in there, the Potato one. The well logs went through her zone of interest, but just the gamma ray. And so she did a well tie and she used that well data as much as she could in the Miocene section. Next slide, please. Okay, and then hit it one more time. Oh, I forgot I have all these animations in here. So this is the area of interest. So she selected a sub-survey of it, and that was just the area where she ran the SOM analysis with Paradise. So this is just a little bit of information on the geologic setting. This is a rift basin. It was a rift basin in the Cretaceous, and then it filled up with some nice, beautiful sedimentary successions. And the area we're looking in is the Miocene, particularly the Moki and Manganese formations. Next slide. Okay, so here we get into a simplified workflow just for part of her thesis work, where she did the well tie, looked for features of interest, figured out some of the lithologies, picked horizons, all the basic early work that you want to do before you start doing an attribute analysis. And then she computed the attributes, divided them into different categories: textural, geometric, instantaneous, and spectral attributes, ran a PCA analysis with the Paradise software, looked at eigenvectors to figure out what were the principal contributors, and then ran a SOM analysis. After that, she did some testing and validation and the analysis and interpretation. And if you could go to the next slide. So here is what some of the data looks like and the features of interest in seismic data. So we've got a vertical section on top and a time slice below. And what you can notice is that she put little boxes and interpretations around certain seismic facies, which were of interest to her that she noticed in the seismic amplitude. So once recognizing some of these features, traditionally this would help steer us in picking out which attributes to use, but we wanted to let PCA do that on our own and see what it came up with. So if you could hit the next slide. So here are the PCA results. So she ended up putting in 28 seismic attributes, and they're all listed there. She let PCA do its thing, narrow down the dimensionality of the data, and she ended up picking out 9 seismic attributes that had the highest levels of independence. And so with that, they represent most of the variability in the data. And so you can see they're listed down there: the cosine of instantaneous phase, the original amplitude envelope, some GLCM attributes, and then a couple curvature and the sweetness. Next, please. And you could click through these. So here she first looked at her area of interest, neuron by neuron, like a nice thorough analysis, trying to see which neurons, which multidimensional attribute combinations were giving her some interesting results and what we would think are geologic features. And so just to point out quickly at the, I can't quite read these, but you can see that some of them have more geologic shapes, and then other neurons are essentially empty or kind of just picking up some of the edge noise. And so these were ones that you could quickly identify as not being important in helping the interpreter understand the channel architecture. And so next we're showing a box where you can kind of see the vertical section and a time slice of some of the more interesting attributes, neurons that we selected. And then if you could click a couple more times to bring everything up. And so zooming in, you can see she ended up selecting 6 neurons. And then with her amazing stratigraphy, she is a student of Dr. Slatt, so she's great at understanding sedimentology and stratigraphy. She went through in detail the neurons to understand the channel architecture. And so you can see here, she thought that neuron 1 was most likely related to silty muddy bars. The yellow ones seem to more likely represent sheet sands, the brown ones sandy bars, pink overbanks or levees, and then the blue ones seem to have the characteristics of more chaotic flows and mass transport deposits. So we thought this was really interesting to be able to tie single neurons to different elements of the channel architectures in the deep water system. Next, please. Yeah, and then, here we're just kind of showing how that fits in more of a schematic with the layered channel fills that you can see in kind of the green and yellow on that last slide. All right, so here's just a few more results, just showing the difference of what SOM analysis can reveal compared to our standard amplitude data. I always find it great to compare our machine learning results compared to the seismic amplitude data, just so you can see how much additional information these methods can provide. And so we've got some time slices and vertical slices showing the difference. And then as well as some different colored arrows that point out some of her interpretations. And if you'll hit this one more to bring up these. So here's kind of the analogs or schematics of what we would expect in this type of deep water system. And so you can start to see what might be some scroll bars, different parts of the channel complex, the MTDs, and the more chaotic by the red arrow. Next slide, please. Oh, yeah, so there's Corellia. Their magnifying glass. So just to conclude, if you could hit it about 5 times, it'll bring up 5 different sentences. And then one more, I think. Okay, so these are some of the main conclusions of Corellia's study. I want to highlight the 3rd and 4th bullet point because they're more related to the SOM and PCA analysis. And so what we found is that PCA did a great job in reducing the dimensionality of the attributes that we were using to let us use a smaller data set that in itself contained most of the variability in the data. And it was also the quickest way to explore a data set. So it was much more time efficient than the second part of her master's thesis, where she went through and did a user selected attribute study to compare the results of SOM between when the PCA did it and when Corellia did it as an expert sedimentologist. So PCA is great for doing your quick first look at the data set. So the machine learning helps us save time, but it's still really important to have the interpreters to validate the data. So we are still important as geologists and geophysicists, and we don't think the machines will replace us yet. All right, so if you go on to the next slide, I will quickly cover the last case study that I wanted to show. So this is the second portion of Julian Chenin's master's thesis, where he's looking at undersaturated gas. Next slide, please. and he's typing this up now so that he can defend next month. All right, so just to kind of quickly summarize, some of you guys may have heard of the term Fizz gas. That's kind of a nickname, but what we're referring to is gas saturated reservoirs that are undersaturated or have a low saturation of gas, so they're not economically viable in the hydrocarbon scheme of things. Of course, there's motivation for de-risking and avoiding drilling uneconomic process. And so he used Paradise software, PCA, and SOM analysis to try and see if he could differentiate in areas where we have a saturated reservoir and an undersaturated reservoir. And so the first example I'll show, again, where he kind of refined his methodology and then tried to apply it to different areas. He did most of his work on this King Kong Lisa Ann prospect, or drilled prospects that are in the Gulf of Mexico in the Green Canyon area, if I'm remembering correctly. And so in that upper vertical slice on the left-hand side, you can see the bright amplitudes that are related to the King Kong prospect. This one was fully saturated, a successful economic well. And then if you just move up dip a little bit, we have the Lisa Ann prospect, which amplitude-wise looks very similar. It's against default, so always a little riskier, but still retain those brighter amplitudes. And so in this area, the company drilled the well and they found that it was unsaturated and uneconomic. So the seismic data, we're looking at it and it's telling us, hey, these two things look similar seismically, but they're actually not in terms of their gas saturation. And so that was the puzzle I sought him out to solve, to see if SOM analysis could help us differentiate between these two reservoirs. And then we also applied this, kind of shown below in the Ursa, so the lower vertical section, the Ursa reservoir, which is also in the Gulf of Mexico. And then just last month, he looked at applying these methods to the Scarborough field off of in the Carnarvon Basin on the northwest shelf of Australia, so moving across the world. Next slide, please. Okay, so the crux.
Hang on, sorry, I think I skipped one.
Yeah, you did. It's kind of an important theory one. So
hold on a second.
That's okay. I think you went the wrong way.
Let's see that.
So 42. Go to 42.
42. There you go. Sorry about that.
That's okay. So just to spend 5 seconds talking about the theory, with increasing gas saturation, the bulk modulus doesn't change too much. So you can see in the green line on the right-hand side that partially saturated gas reservoirs have similar bulk modulus to fully saturated reservoirs. So there's just a very, theoretically, there's a small difference between them. And so this ends up affecting the seismic velocity and therefore the acoustic impedance and the reflection of the seismic data. And so machine learning, we're hoping, is able to differentiate these very small changes. All right, next slide. Okay, I don't know if you guys are looking at it, but I'm going to talk. So here's the geologic background, here we go, of the King Kong Lisa Ann area. So I'm showing that cross-section through the seismic that we already did. So this is deepwater. The King Kong was a structural four-way closure. The Lisa Ann was on the hanging wall of a large normal fault. And this probably ended up being the seal failure that allowed it to be undersaturated. So both of them have similar seismic amplitude anomalies that you could see, but Lisa Ann ended up being uncommercial. Next slide. So, and then you can hit it one more time to show the result. So here's the amplitude section. And then what Julian did is he ran a PCA analysis and a SOM result. This one's showing all of the neurons in the 5x5 that he got. And then if you can go to the next slide. All right, there's where the wells are. Hit it one more time. Okay, and so here here he highlighted just two neurons, neuron 3 and neuron 4. And so what we noticed here is that these two neurons seem to show that there is something slightly different between the King Kong prospect and then also the saturated, undersaturated Lisa Ann prospect. So now if you'll go to the next slide. So what he ended up doing, and hit it one more time, is he took the same parameters and the same, keep hitting it a couple of times. And then once more. Thank you. Okay, so he ended up taking the same attributes and trying to repeat these results in the Ursa field, which is nearby in the Gulf of Mexico. And what's interesting about the Ursa field is there's some well-logged data available there in a study that Fred Hilterman did a while back. He was able to point out, as you can see on the right, that certain reservoirs were more fizz prone, so undersaturated, while other ones were full of oil. And so you can kind of see these different, I'm using my mouse to point this out, but you can see the different higher amplitudes related to these different hydrocarbon reservoirs. And so what's cool about this study is that now instead of comparing two fields that are separated by a few miles, now we can look at reservoirs within the same wellbore. And so using the same attributes as before with the King Kong Lisa Ann, we get the SOM result that's shown on the left. And then if you can go to the next slide, what he did is he highlighted perfect. Just two of those neurons that seem to highlight the more oil-prone reservoirs that end up being more pronounced in the SOM analysis. I should mention here, because I see the words probability threshold, is that Julian really used the probability threshold capabilities of the Paradise software for both this undersaturated gas project and his hydrates, because the probability of either of those happening is kind of on the lower side. So he looked for what was less probable, if I'm saying that correctly. And so what I'm just trying to show here is that we have some different results depending on if they were fizz related or oil related. So they were still pretty optimistic about this. So going on to the next slide, last month or so, Julian started trying to apply this to a Scarborough field offshore Australia to see if he could use the same attributes and get similar results. And so what's interesting about this is we're working in a totally different geologic setting. Some work with the Scarborough field believes it's undersaturated. We were talking to somebody at AAPG, Julian was, where he showed this work, and they were suggesting that there's probably some sort of seal failure here that led to the undersaturated gas in this area. And so if you could go to the next slide. Okay, and then hit it one more time. So here's the amplitude section, kind of outlined in black is the 50% saturation outline from a previous study, Ray et al. In 2014. So that kind of shows roughly where we've got more of the undersaturated gases. And so showing the full SOM result, I think if you click it one more time, it will show us just selected neurons. Julian selected just 3 neurons that seem to really highlight where in that amplitude anomaly you have some of the undersaturated gas. And so the results here, with playing around with the different neurons and changing some of the parameters, Julian noticed that we don't see a great discrimination between the low and high saturated gas zones. And so that kind of is telling us that there's something different going on in the rocks in this area in offshore Australia versus what we were able to replicate in the Gulf of Mexico. If you could go on to the next slide. So the next slide shows the different neurons that Julian had selected as being important to identifying the undersaturated gas reservoirs, as well as the attributes and their neuron in total independence. And if you click a few times, what you'll notice is that the envelope tended to be one of the most important neurons, and then sweetness the second. And so we're still trying to figure out some of these results and exactly what they're telling us between the Gulf of Mexico wells and fields and the Scarborough fields. But we're seeing some consistencies between the two. But right now, I don't think we have super definitive ideas on what's going on. But some analysis does seem to be showing us in some cases that we can qualitatively tell the difference between undersaturated and saturated gas reservoirs. So if you go one more slide, I think this was one of my almost last slides. Yeah, and click it a few times to bring up all the pictures. So where we're at with this SOM analysis and undersaturated fizz gas conclusions is that we're seeing more qualitative differentiation, but it seems to just be working primarily for the GOM data set. So we don't have confidence that this method is transferable to other parts of the world with different rocks and tectonics and properties. So it didn't work well using the same technique in the Scarborough field. And then if you could hit it one or two more times. Cool. Yeah, and so this is just kind of like some summary figures of what we were able to see, and then hit it a couple more times. Got a lot of animations on this one. So just kind of highlighting the King Kong and the Lisa Ann, and then if you hit it one more time, I think it should show Scarborough on the results. Nice. So that's where we wrap up on this case study. And then if you could click the slide one more time, we of course want to acknowledge geophysical insights for providing the University of Oklahoma with Paradise software that has allowed us to do these studies as well as a few others. We're with the School of Geosciences. Schlumberger provided us some software, the Patrol software. We're part of ASPE, I'm part of ASPE, so we're using ASPE software. Consumers Energy gave us the reef data, and then New Zealand Petroleum Minerals and GNS, and then also the USGS provided us with some other free public data sets.